Welcome to our video analysis of the Big Bang, the origin of the universe. In this video, we will explore how the Big Bang started it all, from a singularity to the continuous expansion of the universe. Let's dive into the scientific evidence supporting this theory, the wonders of space and time, and the challenges that the Big Bang theory currently faces. Don't forget to subscribe, like, and share the video to stay updated with more exciting content. The Big Bang is the most widely accepted theory about the origin of the universe, explaining how the universe began from a singularity and expanded to its current size. In this study, we will explore the process of the Big Bang, the scientific evidence supporting this theory, and the challenges the Big Bang theory is currently facing. The Big Bang is the most widely accepted scientific theory regarding the origin of the universe. According to this theory, around 13.8 billion years ago, the universe began from a singularity, an incredibly small point with extremely high density and temperature. From this singularity, the universe underwent a powerful explosion, spreading matter and energy in all directions and continuously expanding to its current state. This process marked the formation of space, time, and all cosmic structures, from basic particles to massive galaxies. Evidence such as the expansion of the universe, cosmic background radiation, and the distribution of elements in space all support the Big Bang theory. The Planck epoch and expansion. The Planck epoch is the earliest stage in the formation of the universe, occurring immediately after the Big Bang, approximately 1,043,101,043 seconds after the event. During this phase, the current laws of physics, including relativity and quantum mechanics, are not fully capable of explaining what happened. At this incredibly brief moment, the density and temperature of the universe were so high that all fundamental forces, gravity, electromagnetism, strong and weak nuclear forces, might have unified into a single force. Right after the Planck epoch, the universe began a rapid expansion phase known as cosmic inflation, where space expanded at a rate faster than the speed of light. This inflationary period established the initial structure of the universe and helps explain why the universe today has such high uniformity. This expansion continues to this day, with galaxies moving farther apart due to the influence of dark energy. Inflationary epoch. The inflationary epoch is a critical phase in the early development of the universe, occurring immediately after the Planck epoch and lasting from approximately 1,036,101,036 to 1,032,101,032 seconds after the Big Bang. During this phase, the universe expanded at an extremely rapid rate, faster than the speed of light, increasing its size by billions of times in just a fraction of a second. Cosmic inflation helps resolve several key issues in cosmology, such as the flatness problem and the horizon problem. This inflation also caused initial structures to become more uniform, laying the foundation for the development of galaxies and star systems. Eventually, the inflationary phase ended as the universe cooled, and fundamental forces began to separate, leading to a slower but continuous expansion that persists to this day. Evidence for the Big Bang theory. 1. The expansion of the universe. The expansion of the universe is one of the most significant discoveries in modern astronomy and plays a central role in the Big Bang theory. This concept was first discovered by astronomer Edwin Hubble in 1929 when he observed that galaxies are moving away from each other. This expansion not only provides evidence for the theory of the universe's origin, but also raises questions about the future of the universe and the nature of dark energy. The expansion of space. The expansion of the universe is not the physical movement of galaxies through space, but rather the space between galaxies that is expanding. The common image of a balloon or rising bread with raisins helps us visualize this expansion. As space expands, the galaxies in the universe move farther apart from each other, but they themselves do not move through space in the way that an ordinary object moves. Hubble constant. The rate of expansion of the universe is determined by a quantity known as the Hubble constant. This constant measures the speed at which galaxies move away from each other in relation to their distance, expressed through the formula V equals h0 divide equals h0 times divide equals h0 d, where v, the speed at which a galaxy is moving away, h0, the Hubble constant, d, the distance between the galaxy and the observer. Evidence for the expansion of the universe. Redshift effect. As galaxies move away, the light from them is stretched toward longer wavelengths due to the Doppler effect. This creates a phenomenon known as redshift. Observations from Earth show that the farther away a galaxy is, the greater its redshift, which means that more distant galaxies are moving away from us at a higher speed. Cosmic microwave background radiation. Cosmic microwave background radiation, discovered in 1965, is the remnant light from the early period of the universe. The CMB has the same temperature and appears uniform in all directions, indicating that the universe was once in a hot and dense state before it began to expand and cool down to its current form. The abundance of light elements. The abundance of light elements such as hydrogen, helium, and lithium in the universe matches the predictions from the Big Bang model of an expanding universe. The alignment of this ratio with today's measurements provides supporting evidence for the Big Bang theory and the expansion of the universe. Models of the expansion of the universe. Closed universe model and Big Crunch. In this model, if the density of matter in the universe is sufficiently high, gravitational forces could cause the universe to stop expanding and begin to contract, leading to a major collapse known as the Big Crunch, where the universe collapses back into the original singularity. Flat universe model and slowing expansion. If the density of matter is close to a certain threshold, the universe will continue to expand forever but at a gradually slowing rate. The universe will neither collapse back nor expand infinitely at an accelerating pace. Open universe model and infinite expansion. If the density of matter is low, the universe will continue to expand infinitely at an accelerating rate, leading to the dilution of matter in the universe until galaxies no longer interact with each other. The role of dark energy in expansion. Observations from the late 20th century show that the universe is expanding at an accelerating rate. This was unexpected because, under conventional reasoning, the gravitational pull of matter in the universe would slow down the expansion. To explain this phenomenon, scientists proposed the concept of dark energy, a mysterious form of energy that makes up about 68% of the universe's energy and is responsible for the accelerated expansion. The nature of dark energy remains a significant mystery for scientists. Some theories suggest that it is an inherent property of space or related to undiscovered fundamental particles. Regardless of its nature, the presence of dark energy plays a crucial role in the current rate of expansion of the universe. The future of the universe and expansion. The future of the universe depends on how dark energy and other factors will influence its expansion. There are three main scenarios for the future of the universe. The Big Freeze. If the universe continues to expand indefinitely at an accelerating rate, galaxies will move away from each other to the point where they no longer interact, and stars will gradually exhaust their energy, resulting in a cold and dark universe, known as the Big Freeze. The Big Rip. If dark energy increases dramatically, it could push the universe to expand at such a rate that it destroys all structures of matter within the universe, including galaxies, stars, planets, and ultimately atoms, leading to a sudden end known as the Big Rip. The Big Crunch. In the case where dark energy decreases and gravitational forces become dominant, the universe may stop expanding and begin to contract, returning to its original dense state, leading to a cycle of collapse and potential rebirth. The expansion of the universe is one of the most important and intriguing discoveries in cosmology. This discovery not only sheds light on the origin and evolution of the universe, but also opens up questions about the nature of space, time, and dark energy. Although the future of the universe remains full of mysteries, its expansion continues to be an important topic of research, helping humanity better understand its place and future in the vast universe. 2. Cosmic microwave background radiation. Cosmic microwave background radiation is the electromagnetic radiation that permeates the entire universe and is a remnant from the early universe, approximately 380,000 years after the Big Bang. CMB was discovered in 1965 by two scientists, Arno Penzias and Robert Wilson. This discovery provides strong evidence for the Big Bang theory and helps scientists gain a better understanding of the origin and structure of the universe. The formation of CMB. The early universe and the plasma era. About 13.8 billion years ago, the universe was in an extremely hot and dense state. Electrons, protons, and photons could not combine due to the high temperature and dense density, creating a sea of plasma in which photons were continuously scattered by free electrons. This made the universe opaque, preventing light from moving freely. The recombination era. After about 380,000 years, the universe had cooled sufficiently for protons and electrons to combine into hydrogen atoms, a process known as recombination. As electrons combined with protons to form atoms, there were no longer free electrons to scatter photons. Thus, light could move freely throughout the universe, resulting in the cosmic microwave background radiation that we observe today. CMB radiation and the expansion of the universe. The light from that time has been redshifted due to the expansion of the universe, changing from its original visible or infrared light to the microwave wavelengths that we measure today. The current average temperature of the CMB is about 2.725 Kelvin and is primarily detected in the form of microwaves. Evidence and significance of CMB. Evidence supporting the Big Bang theory. The discovery of the CMB aligns with the predictions of the Big Bang theory, which posits that the universe was once in a hot, dense state and has gradually cooled over time. Without the Big Bang, we would not observe the uniform background radiation throughout the universe. Homogeneous distribution of CMB. The CMB is present in every direction in the universe with nearly uniform intensity, supporting the hypothesis that the universe was initially in a homogeneous and isotropic state. However, detailed measurements of the CMB reveal small fluctuations in temperature, which are signs of slight inhomogeneities in the initial density of matter, laying the groundwork for the formation of large structures such as galaxies and galaxy clusters. Temperature fluctuations in CMB. These small fluctuations, also known as temperature anisotropies in the CMB, are the result of variations in the density of matter in the early universe. These regions formed the initial seeds of today's galaxies and galaxy clusters. Studying these fluctuations has helped scientists gain further insight into the formation of large structures in the universe. Discoveries from CMB. the COB project and the discovery of small fluctuations in 1989, NASA's COB spacecraft was launched to make detailed measurements of the CMB radiation. COB was the first project to confirm the existence of small fluctuations in the CMB, demonstrating the very slight temperature variations in the early universe. The MAP project and detailed CMB mapping following COB. The MAP spacecraft was launched in 2001 to create a more detailed map of the CMB. This map revealed the distribution of small hot and cold regions in the early universe, allowing scientists to make more accurate measurements of the age of the universe, approximately 13.8 billion years, and its fundamental components, ordinary matter, dark matter, and dark energy. The Planck project and high-resolution The Planck spacecraft from the European Space Agency, launched in 2009, provided higher-resolution images of the CMB. Planck's data has allowed scientists to gain a clearer view of the structure of the universe and to make more accurate calculations of cosmological parameters such as the Hubble constant and matter density. The role of CMB in modern cosmology. Determining the age of the universe. Studying the CMB allows scientists to accurately calculate the age of the universe, which is approximately 13.8 billion years. By analyzing the temperature fluctuations in the CMB, they can infer the stages and historical processes of the universe from the time of the Big Bang. Components of the universe. The CMB provides important information about the composition of the universe, which includes approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. This helps scientists gain a better understanding of the roles and effects of these components on the expansion of the universe. Measuring the geometry and structure of the universe from the CMB. Scientists can also determine the overall geometry of the universe. CMB data indicates that the universe is nearly flat, which has significant implications for theories about the future of the universe and space-time models. Cosmic microwave background radiation is a groundbreaking discovery in the fields of astronomy and cosmology, providing us with valuable insights into the early universe and its formation process. The CMB not only confirms the Big Bang theory, but also enhances our understanding of the universe's structure and composition. However, many questions remain unanswered about the nature of dark energy, dark matter, and what happened before the Big Bang. Research on the CMB will continue to play a crucial role in humanity's journey to explore the universe. 3. The ratio of light elements in the universe. The ratio of light elements in the universe, particularly hydrogen, helium, and trace amounts of deuterium, helium-3, and lithium, is one of the most significant pieces of evidence supporting the Big Bang theory. Immediately after the Big Bang, the universe was in an extremely hot and dense state, allowing nuclear reactions to occur and producing light elements. Studying the ratios of these elements helps us better understand the conditions in the early universe and provides further evidence of the formation and evolution of the universe. The process of nucleosynthesis in the Big Bang. The early universe. Immediately after the Big Bang, the universe was extremely hot, with temperatures reaching billions of degrees Kelvin. In this environment, particles such as protons, neutrons, electrons, and photons existed freely and continuously collided with one another. About 1 second after the Big Bang, the temperature of the universe decreased, allowing neutrons and protons to begin interacting and combining to form atomic nuclei. The primordial nucleosynthesis process from about 1 second to 3 minutes after the Big Bang, as the temperature of the universe continued to decrease, nuclear reactions occurred at a high intensity, allowing for the creation of light elements. These reactions led to the formation of hydrogen nuclei consisting of just one proton, deuterium, one proton and one neutron, helium-3, helium-4 2 protons and 2 neutrons, and a very small amount of lithium-7. The end of the nucleosynthesis process as the temperature continued to drop below the levels required for nuclear reactions to occur. The primordial nucleosynthesis process came to an end, and the ratios of light elements remained nearly unchanged to this day. Approximately 75% of the mass of the early universe was hydrogen, about 24% was helium, and less than 1% comprised other light elements such as deuterium and lithium. The ratios of light elements. Hydrogen makes up about 75% of the mass of the universe and is the lightest and simplest element, consisting of just one proton and one electron. In the early universe, most hydrogen existed in atomic form or as ions when electrons were stripped away due to the high temperatures. Helium accounts for about 24% of the mass of the universe. A helium-4 atom consists of 2 protons and 2 neutrons, forming a very stable nucleus. The significant presence of helium serves as evidence for the nuclear synthesis during the Big Bang, as the high temperatures and pressures allowed protons and neutrons to combine to create this element. Deuterium, an isotope of hydrogen with 1 proton and 1 neutron, makes up only a very small amount of the universe. Approximately 0.001% of its mass. Deuterium is highly sensitive to high temperatures and can easily be broken down, making the current abundance of deuterium in the universe an important indicator of the temperature conditions during the period of nucleosynthesis. Helium-3, a lighter isotope of helium-4 with 2 protons and 1 neutron, also constitutes a very small amount. Although helium-3 is less stable than helium-4, its abundance in the universe aids scientists in studying the nuclear processes that occurred shortly after the Big Bang. Lithium is the lightest element formed from the Big Bang and is present in a very small proportion. The presence of lithium in the early universe was predicted by the Big Bang nucleosynthesis theory. However, actual observations show that the abundance of lithium is lower than predicted, which remains an ongoing area of research. The significance of the abundance of light elements. Confirmation of the Big Bang theory. The abundance of light elements aligns with the predictions of the Big Bang theory, demonstrating that the temperature and density conditions in the early universe were sufficiently high for nuclear reactions to occur and form light elements. This serves as significant evidence supporting the Big Bang theory, in contrast to static universe models that cannot account for this abundance. Information about the density and temperature of the early universe. The abundance of deuterium, helium-3, and lithium provides important insights into the density and temperature of the universe during the nucleosynthesis period. For example, a high amount of deuterium indicates that the density of the universe was lower in its early stages, as higher densities would have destroyed deuterium through nuclear reactions. Constraints on cosmological models. The ratios of light elements help constrain the parameters of cosmological models. In particular, the observed values of deuterium and lithium can be used to measure the density of matter in the universe and the Hubble constant, thereby improving the accuracy of models that describe the universe. Challenges and open questions. The lithium problem. One major issue in this field of research is the discrepancy between theoretical predictions and actual observations regarding the lithium abundance. Nuclear synthesis models predict a higher lithium ratio than what we observe. This phenomenon, known as the lithium problem, remains an open question and a challenge for scientists. The influence of dark matter and dark energy. The existence of dark matter and dark energy affects how elements form and distribute throughout the universe. Although dark matter does not interact with light elements, it impacts the overall density of the universe and its expansion. Dark energy also influences the evolution of the universe, making the determination of light-element ratios more complex. The ratio of light elements in the universe is strong evidence supporting the Big Bang theory and provides important information about the conditions in the early universe. The ratios of hydrogen, helium, deuterium, and lithium indicate that the universe underwent a period of high temperature and sufficient density for nuclear reactions to occur. However, questions such as the lithium problem remain a challenge for current cosmological models. Studies on the ratios of light elements will continue to play a crucial role in understanding the origins and structure of the universe. The main stages of the universe after the Big Bang. The atomic era and the formation of atoms. About 380,000 years after the Big Bang, nuclei and electrons began to combine to form atoms, primarily hydrogen and helium. The formation of atoms allowed light to travel freely through space, leading to the cosmic microwave background radiation that we observe today. The formation of galaxies and stars. Over hundreds of millions of years following the Big Bang, regions of high density began to collapse under the force of gravity, resulting in the formation of the first galaxies and stars. These first stars played a crucial role in creating heavier elements, such as carbon and oxygen. The evolution of the universe to the present. The universe continues to expand and evolve to this day. Galaxies, stars, and planets continue to form and change, while the expansion of the universe continues due to the presence of dark energy, an enigmatic component that accounts for most of the universe's energy. Challenges and limitations of the Big Bang theory. Singularity and the Planck time. The Big Bang theory cannot accurately explain what happened before 1,043,101,043 seconds after the Big Bang, because the laws of physics as we know them no longer apply. This is a contentious issue and requires a new theory to describe these conditions, possibly a theory of quantum gravity. The nature of dark energy and dark matter. The Big Bang theory has yet to explain the nature of dark energy and dark matter, two components that make up about 95% of the universe. Dark energy causes the accelerated expansion of the universe, while dark matter is a crucial factor in the formation of the universe's structures. The problem of infinite space and time. Other questions remain unanswered, such as whether the universe is finite or if it is a cyclical system with multiple successive Big Bangs and Big Crunches. The Big Bang theory is a successful model that describes the origin and expansion of the universe. Evidence such as the expansion of the universe, cosmic microwave background radiation, and the ratios of light elements all support this theory. However, many questions remain unanswered, particularly regarding the nature of dark energy and the initial conditions before the Big Bang. Continued research and the development of new theories will help us gain a deeper understanding of the universe. The evolution of the universe from the Big Bang to the present is a complex series of stages, including the formation of particles, atoms, stars, galaxies, and other large-scale structures. Each stage is influenced by key factors such as dark matter, dark energy, and gravity. The current universe is in a phase of accelerated expansion driven by dark energy, and the future of the universe will depend on how dark energy and gravity interact with each other. This evolutionary process is not only a story of expansion and change, but also the foundation for life and the development of the complex structures we observe today.